Have you ever actually stopped to look at a massive steel cargo ship and wondered, why doesn't it just dissolve? I mean, think about it. Global shipping is absolutely crucial to our daily lives. Almost everything we buy comes across the ocean. But the ocean itself, it's one of the most relentlessly hostile environments on Earth. From the exact second a steel hull hits that salt water, an invisible, non-stop battle begins. It is quite literally a war to keep the ship from disappearing straight back into the Earth.
So, welcome to this explainer on marine corrosion and defense mechanisms. Today, we're going to unpack this epic high-stakes war between relentless natural forces and human engineering. We'll be using the science of electrochemistry to understand exactly how these massive ships actually survive the sea.
To make sense of this complex electrochemical battlefield, we're going to break things down logically into 5 distinct phases: the anatomy of corrosion, the specific types of marine corrosion, cathodic protection systems, our first lines of defense, and finally, what happens when those defenses fail.
All right, let's jump right into Section 1, Anatomy of Corrosion. The battle begins.
Okay, so before we can defend a ship, we really need to understand the fundamental requirements for the enemy to even launch an attack. For corrosion to happen, 4 absolutely non-negotiable components must be present. Essentially, they form an electrical circuit. First up, you need an anode. That's the metal that is actually corroding and losing mass. Second, a cathode, which provides the surface for the environment to react. Third, you need an electrolyte. In our case, that's the aqueous environment of seawater that allows ions to travel. And fourth, an electrical connection that lets electrons flow between the anode and cathode. Here's the kicker, though. Remove just one of these 4 things, the attack stops completely.
Now, a super crucial concept here is the surface potential of metals. When a metal just sits in an aqueous environment, it establishes its own electrical potential. As you can see in this electrochemical hierarchy, the more positive metals are considered noble, and they're much less reactive. On the flip side, the more negative metals are called base metals, and they are highly reactive. When a ship is exposed to seawater, engineers use this exact series to predict which metal is going to sacrifice itself when 2 different metals are connected.
So why should you care about all these microscopic reactions? Well, because global shipping relies on massive vessels sailing through an environment that is constantly trying to accelerate this attack. High oxygen areas, like near bellmouths, they see much faster decay. Heat is a massive catalyst too. Areas right next to engine rooms or heated cargo tanks, they corrode way faster. Plus, the high conductivity of seawater, which is just packed with dissolved ions, speeds up that electrical flow we talked about. You've also got destructive ions like chlorides and sulfur, often from sour crude oil, stripping away natural protections. And finally, pH levels matter immensely. Highly acidic environments will literally chew right through steel. But, fun fact, under highly alkaline conditions, steel actually can't corrode at all. It remains completely unaffected.
Moving on to Section 2, Types of Marine Corrosion. Let's look at the tactical attacks.
The most common type of attack you'll see is uniform corrosion. Just like the name implies, it's a widespread, fairly even loss of metal across a large surface. On a microscopic level, what's actually happening is a continuous, shifting interchange between anodic and cathodic areas over time. Now, because this decay is so widespread and predictable, structural engineers actually find this the easiest form of corrosion to deal with. They can just calculate the expected metal loss and design the ship's structural lifespan around it from day one. But that predictable decay perfectly contrasts with a much more dangerous threat: pitting. Unlike uniform corrosion, pitting is a highly localized, deep penetration. It typically forms where a really small anodic area is totally surrounded by a massive cathodic area. Like, say, when the mill scale on a steel surface gets broken. That tiny broken area instantly becomes the anode and gets aggressively eaten away, creating these deep, hidden holes. It's incredibly dangerous because it can completely compromise the hull's integrity while remaining almost invisible to a casual inspection.
And the ocean has an entire arsenal of specialized attacks ready to go. You've got crevice corrosion, which happens when trapped debris or mud depletes oxygen in a specific localized area, turning it into a highly vulnerable anode. Then there's galvanic corrosion. That kicks in when 2 dissimilar metals are coupled in seawater, causing the baser metal to rapidly decay. Impingement corrosion is particularly brutal. It happens during tank washing when high-velocity fluids literally strip the natural protective oxide layers straight off the metal. And we can't forget stress corrosion, where the deadly combo of structural tension and a corrosive environment simply cracks the steel open.
And hey, just when you think you've accounted for all the chemistry and physics, biology decides to enter the chat. Microbiologically influenced corrosion, or MIC, is this fascinating and highly destructive attack carried out by living organisms.
In deoxygenated environments, like inside ballast tanks, acid-producing bacteria and sulfate-reducing bacteria absolutely thrive. They create these slimy webs, pump out acids and hydrogen sulfide, and can aggressively chew through even highly resistant materials like stainless steel. No steel is entirely safe.
Okay, let's talk defense. Section 3, Cathodic Protection Systems, Active and Passive.
So how do we actually fight back against this invisible army? Well, we fight electrochemistry with electrochemistry. We actively manipulate the potential of the ship itself, forcing the steel hull to become a protected cathode. It's an absolute marvel of engineering that essentially ensures the global supply chain doesn't just rust away beneath our feet. We do this in two primary ways: sacrificial anodes and impressed current systems. Sacrificial anodes are our passive decoys. They are literally blocks of highly reactive base metals, like zinc or aluminum, that we intentionally bolt onto the ship so they dissolve instead of the steel. Then you have impressed current cathodic protection, or ICCP, which is our active defense system, using the ship's own electrical power to forcefully regulate those chemical reactions.
Now, the crucial thing to know about sacrificial anodes is that they come with incredibly strict operational rules. They're specifically designed for uniform wearing and usually only have a 5-year lifespan, which means they absolutely have to be renewed during dry dock surveys. Also, you must never, ever paint them. If you paint an anode, you insulate it, and you've completely ruined its ability to work. And critically for safety, magnesium and aluminum anodes are strictly forbidden in or anywhere near cargo oil tanks. Why? Because if they fall, they can strike the steel, create a spark, and trigger a catastrophic explosion.
Let's move over to ICCP and see how this builds a far more advanced high-tech defense. This system relies on 5 basic components, but the real magic happens in 3 distinct steps. First, an external reference cell measures the exact voltage difference between the seawater and the hull. This is known as the solution potential. Second, a smart electronic controller compares that live measurement to a calibrated internal reference voltage. Finally, the controller delivers a super precise amount of DC electrical current from the ship's power supply out into the water and back into the hull. This current shifts the hull's natural potential to a state where all chemical reactions become purely cathodic. And remember, no anodic reactions means no corrosion. It's just brilliantly effective.
Which brings us to Section 4, the first line of defense: marine coatings. Before we rely on any of that electrical manipulation, we wrap the entire ship in physical armor, protective paint. But here's the catch: paint is completely useless if its foundation is flawed. Surface preparation is arguably the single most critical step in all of marine maintenance. Engineers follow really rigorous ISO blast cleaning standards to prep the steel. ISO SAW 3 is the gold standard here. It means it's visually clean down to a uniform metallic color, totally free of any rust or mill scale. SAW 2.5 is very thorough, allowing only slight staining, and SAW 2 just removes most foreign matter. If you try to apply high-tech, expensive coatings over poorly prepped, rusty steel, the entire system will fail almost immediately.
Once that steel is perfectly prepped, we have to choose our armor. Marine coatings generally fall into 2 categories based on their binders: thermoset and thermoplastic. Thermoset coatings, like highly durable epoxies, come in 2 packs. When you mix them together, they undergo a massive chemical reaction to cure. Once they dry, they form this complex, rock-hard shell that will literally never redissolve in its original solvent. Thermoplastic coatings, on the other hand, are much simpler, 1-pack paints. They dry just by the physical evaporation of a solvent. While they're super convenient for quick maintenance touch-ups, they can easily soften if they're exposed to extreme heat or their original solvent again. But to make these binders truly effective, we load them up with tactical pigments. We aren't just coloring the ship to make it look nice, we're giving the paint highly specialized jobs. Adding zinc powder effectively turns the paint itself into a sacrificial anode, providing galvanic protection right there on the surface. Adding metallic aluminum flake creates a tough, overlapping physical barrier that acts like microscopic shingles to keep water out. And zinc phosphate? That's a chemical weapon. When water hits it, it releases ions that actively shut down both anodic and cathodic corrosion reactions on the steel underneath.
Finally, let's look at Section 5, when defenses fail: coating defects.
Look, even the best chemistry in the world is entirely at the mercy of human application. Spraying these heavy-duty coatings is an art and a science, and simple errors create immediate weak points for the ocean to exploit. If an applicator puts the paint on too thickly on a vertical surface, it sags and drips, completely compromising the barrier. Poor spray technique or using the wrong solvent blend leads to a dimpled, uneven surface we call orange peel.
Over-applying heavily pigmented primers on horizontal surfaces? That causes stress-related mud cracking as it cures. And dry spray leaves these poorly adhered, powdery overspray particles everywhere, which ruins the adhesion of any top coats you try to add later. And the reason engineers care so deeply about these application errors is because fixing them is absolutely brutal. As the source material bluntly points out, dealing with issues like sags or mud cracking often requires, and I quote, removing the coating completely to achieve a clean surface and reapplying the coating system. There are very rarely easy touch-ups in a marine environment. If you compromise that armor, you almost always have to strip it all the way back down to bare steel and start the whole process over.
So to sum up everything we've explored in today's explainer, the battle against marine corrosion is a relentless, perpetual war of attrition. From perfectly balancing those electrochemical potentials using sacrificial anodes and ICCP to meticulously blasting steel and applying complex thermoset polymers, it is never, ever a set-it-and-forget-it scenario. It requires constant vigilance, strict adherence to chemistry, and highly precise engineering just to keep these ships intact and afloat.
Which leaves us with a pretty fascinating final thought. If rust truly never sleeps, and our current methods require this constant, high-maintenance battle, what kind of crazy new technologies will we need to protect the ships of tomorrow? Will we engineer smart, self-healing paints? Or maybe invent entirely new alloys that just rewrite the galvanic series altogether? The oceans certainly isn't going to get any less hostile, which means our engineering has to keep evolving. Thanks so much for diving into this explainer with me. Keep exploring and keep questioning how the incredible world around you is actually built.